Alright, this is a quick demonstration of my final project for digital electronics. I'm going to try to keep this as non-technical as possible. Maybe I'll do a more in-depth dive. Basically, we were tasked with assembling a digital circuit project using a list of required components. You got more point value depending on how many components you used. And the premise of mine was a 2-output temperature controller. The inspiration for which came from the idea of a fermentation cabinet, which is an enclosure used to ferment food products like kombucha, sourdough, beer, the yeast of bread, the spores of mushrooms, etc. Interestingly enough, all those microorganisms thrive at an optimal temperature of 86 degrees Fahrenheit or 30 Celsius. So that's what this is designed to emulate. I have a red LED to simulate a heating element, got a digital AC fan for the cooling element. I have 2 optocoupler relays to isolate the household 120 volt AC power, which drives the light and the fan, from the 5-volt control voltage that comes from the digital trainer board. I'm using a really common TMP36 analog temperature sensor. The TMP36 uses voltage. I believe the sensor gets more or less resistance as the temperature heats or cools, which changes the voltage, and I think it has a proportional voltage, like 20 millivolts equals 20 degrees Celsius. We're using Celsius because it's a smaller number for the same range, so it's easier to set my binary set point. I'm using an Arduino, which could probably do the whole project and more, but all it's going to do is take the input from the analog temperature sensor. Arduinos have built-in analog to digital converters. So using a little bit of code, it's going to take an analog reading and spit out 2 digital values to the heart of my digital circuit, which is using 2 7447 decoders. They're going to take a binary coded decimal, which the Arduino with some code is going to take the binary temperature and change it a little bit so that these 2 chips can display a number 0 through 9 on these 2 7-segment displays. And by splitting them up, it's going to be able to properly read the temperature for us. The other value is going to be straight binary, and it's going to give that straight binary value to the other core chip, which is 2 7485 comparators, which compare 2 number values. They're going to compare the binary from the temperature with the binary from the set point. We're going to choose a temperature value in binary, and the comparator is going to say, is the temperature less than the set point, is it equal to the set point, or is it greater than? And depending on which, it's going to trigger the correct output. So if the temperature is colder than my set point, the heating element will come on. If it's warmer, the fan or cooling element will come on. And if it's equal, neither element will come on. So let's power this up and see if we can get it to run through the cycle. So first, I've just powered on the Arduino, and we're going to see its readout on the serial monitor. There you can see the exact Celsius temperature, its conversion into binary, and its conversion into binary coded decimal. Now we'll turn on the rest of the circuit and see how it interacts. Knowing the temperature is around 19, I'm going to set my set point to 21. 16 plus 4 plus 1. And we should see the heating element come on right away as I turn it on. There you go. Display shows it's at 19 and our heating element is on. So if we can get the temperature to get up over 21, we should see this turn off. So I'm going to hope my fingers are enough surface temperature to make this go up. So immediately it jumped to 24, killed the light, and turned the fan on. If I let go and we watch this drop back down, it's on 5-second loops, so every 5 seconds it scans the temperature. We might get to see it hit 21 and shut both off. 21, both are off, and when it drops again, you're going to see the light come back on. There you go, 20, and the heating element comes back on. So that's the demo, 2-output temperature controller.